Okay, welcome to the experiment 1 for Physics 203. This is the lab that accompanies Physics 101 and Physics 201. Just two things about this experiment before we get started. First, there is an additional requirement that's not in the lab manual, and I will show you that in just a few minutes. I want you to calculate the standard percent error and the standard error for the length, width, and height of your rectangular object, and the standard error and the standard percent error of the volume of that object. I'll show you an example on how to do that. And then the second thing is that there is one practical application within this lab that you don't get to do your hands on, and that's for a vernier caliper, but you will need to know how to use a vernier caliper for future labs, and you'll get to do that in the class, and you'll be expected to do that on the midterm and final, but you just sort of have to use a simulator right now, but we'll see that again in the lab. So again, this lab is there just to introduce you to how we take measurements, and I think that you probably think you know how to measure things, but many people do not really know how to measure things, even with something as simple as a ruler. And then, of course, many people do not know how to use a vernier caliper. But, you know, for all of you students, I think, especially for you biology students, a vernier caliper can be very useful to taking measurements in the field. So it'll be useful for you to know how to use that device. And then all scientists need to know how to deal with measurements and uncertainty in our measurements. So first of all, when we talk about errors, I like the word uncertainty, because an error implies that you've made a mistake, and even if you make no mistakes in your measurements, you're still going to have uncertainties, and those uncertainties will include two different types. You're going to have systematic uncertainties, and systematic uncertainties are usually due to problems that you have in taking your measurements. It means that your instrument is not calibrated properly, or they're otherwise flawed in some way. And they would generally produce errors that are consistent in the amount and direction. That means that it's always going to measure too big or it's always going to measure too small. Usually, not necessarily, but usually. So if you used a meter stick that was only 99 centimeters long, or 0.99 meters, then every measurement that you made would just be a little bit too big. Right? That all of your rooms would just be a little bit smaller because the measuring device that you used was not right. And then random errors are even more common, and these are just small variations in the data. And it's not necessarily that you're making a mistake, it's just that maybe you're using a tool that is not ideal, or you just have some inherent uncertainty in the tool that you're using. When we're presenting these errors, the random errors will usually be represented as x, where that's the average x bar, x with a bar over the top, plus or minus, and then the uncertainty will be a number like that. And this is the Greek letter sigma. We often use that letter for uncertainty. This plus or minus means that if I have a value for x right here, and that certain value, then it might have an uncertainty that is in either direction. So if you imagine this is on an axis, this is my x. So if this is 2, then it might be plus or minus 1, so this would be 3 and that would be 1. So the measurement for x could be here, or it could be anywhere in between those. So we use that for random errors, the plus or minus, because they can be in either direction. But systematic errors, on the other hand, might be just in one direction. So x plus sigma or x minus sigma. We don't encounter these types of uncertainties in this lab very often, but as you move on into your curriculum in whatever degree plan you are, chemistry or biology or geomatics or whatever, that you might begin to see these types of uncertainties in data that you're dealing with. So the first, just a few definitions. I think that almost everybody here knows what a mean is, or not that I'm mean, or that other people at the university are mean, although they might be. I'm not mean, but other people might be mean. But mean is just a fancy word for average, although I guess it's not fancy, it's shorter. So this is our definition for average. It's the sum of the individual measurements divided by the total number of the measurements. So let's say that I take measurements for x. I take them 3 different times and I get 3 different values. And by the way, when you're taking measurements in this class, you want to take the measurement and then set down your device or your object or whatever you're measuring, and then pick it back up again and try to look at it with a fresh set of eyes. So you should have some difference in the measurements that you're taking. So x, let's say that I take measurements and I get 2, 4, and 6. And let's say, I don't know, these are meters. Or to say centimeters. It doesn't really matter what the units are. So if I have 2, 4, and 6, I mean, somebody might be able to look at that and tell me what the average is because they're sort of evenly spaced. But if I want to know what the average is, I would say x is equal to the sum of those individual values, 2 plus 4 plus 6, divided by the total number. Right, there are 1, 2, 3 values there. So that's 12 divided by 3, which is equal to 4. So x bar, the average or the mean, is equal to 4. And then the next thing that we need to do is to figure out what is the deviation for each of these single measurements. And that's there, xn minus x bar. So I'm going to write this down here. Usually we let deviation be the Greek letter delta. It doesn't really matter for this, but I just want to know what is the deviation. And my deviation here is going to be 2 minus 4. That's actually minus 2. I'm sorry. No, that's not right. I'm being correct. Actually, all these signs are going to go away. So I would say 4 minus 2, so that would be 2. 4 minus 4 would be 0, and then 4 minus 6 would be negative 2. So those are my deviations for each individual measurement. 2, 0, and minus 2. And then in the third step, this is 1, 2, 3. In the third step, I want to figure out what is the standard error. And to find the standard error, I use this formula. By the way, in this class, you'll have every equation that I ever give you. So don't try to memorize these equations. In fact, that's generally true in science, that it's not really about memorizing equations. It's about the process of science and the scientific technique that you approach in taking measurements. So my point is, don't try to memorize this equation. I don't know that I could memorize it. But so my standard error is the sum, that's what that sigma symbol means, of the absolute value of the deviation squared. So this is going to look like this. When I do this example for these 3 measurements, it's going to be the sum. That's going to be 2 squared plus 0 squared plus negative 2 squared divided by 3 times 3 minus 1. And so that standard error is 4 plus 4, 8 divided by 6, the square root of 8 divided by 6. And I get 1.2. Actually, I would represent this as 1 with 1 significant figure. So when I write my value for x, I would say that x is equal to x bar plus or minus the standard error, which is going to be my mean, which is 4, plus or minus 1 centimeter. So if I have a value for x that is equal to 4, then I would have my data point here, but then I would have error bars on that are 1 centimeter in either direction. Okay, so that's how we calculate standard error and the deviation and the mean. That is something that you will need to do on the midterm and the final. And it is something that we will do in other labs. So make sure that you get that in this lab, that you know how to calculate the standard error. And again, we're going to give you equations, so don't worry about memorizing the equations, but you just need to know how to go through that process. Now there's something that's not in your lab manual, and that is the standard percent error. And I want you to know how to do that. And then I'll show you one other thing that you need to be able to do. Sorry, we had taken this out because this lab used to be kind of long, but now we've taken some other stuff out, so now we're putting this back in. This is a very important skill. So I'm going to say standard percent error. I'm going to call that for short SPE. And so the standard percent error is equal to the standard error divided by the average times 100%. So let's go back to our values we had before. I had x bar was equal to 4. And then my standard error was equal to, I think it was 1, right? Yeah, 4 plus or minus 1. So if I want to know my standard percent error, I would say 1 divided by 4 times 100. That tells me that my standard percent error is 25%. So I have a 25% standard percent error. That means that the percent of the total amount of my X bar is 25%. I'm 25% uncertain about what that value is. Now let's say that I have an object. Let's just do the area. Say I have an object and I want to know its area. The area is equal to a length times a width. And actually, you're going to have to do this for volume. So you're going to have to do length times width times height for a rectangular prism for some device that you will, object that you will measure. So if my area is length times width, let's just give some values for this. Let's say that my length is 4 plus or minus 1, and my width is, let's do 4 plus or minus 2. So I can calculate the area of this object. It's equal to 4 times 4, which is equal to 16, whatever, meters squared, whatever my units are. But what is my uncertainty in that area? Now, whenever we're calculating the uncertainty of a formula like this, when we're multiplying the values, when we're multiplying two or more numbers, the SPE is given by this. So the standard percent error of the area, right, because my area has some uncertainty in it, because my length and my width, they have an uncertainty in it, is going to be equal to the square root of the standard percent error of the length squared plus the standard percent error of the width squared. So if I want to do that, I can find SPE up here. I'm not going to do it. I'm not going to write out the numbers, but we've already done the SPE for this value, the 4 plus or minus 1. That was 25%. Right, 1 divided by 4 times 100. Here, this is 50%. I would say 2 divided by 4 times 100. That's 50%. So this would be the square root of 25% squared plus 50 squared. And then that would give me my standard percent error. I get 56%. Okay, so that's my SPE, or my standard percent error for the area. Now, if I want to find SE, which is really what I want, the standard error, well, I need to go back to that original equation that I gave you. SPE is equal to X bar divided by standard error times 100. And then I want to solve for the standard error. And so the standard error, if I rearrange this equation, is going to be X bar times 100 divided by SPE. So I have X bar was 16. Just to remind you where that came from. That came from right here. Times 100 divided by my SPE, which is 56%. We're being a little loose with our percentages. We're just sort of using that as a number. So that's 1600 divided by 56, and I get 20. Hold on. Okay, I made a little mistake here. Hopefully you caught that along the way. I wrote the SPE equation incorrectly. So let's do that. Just notice, because my standard error just seemed way too big. And sometimes when you're in science, you'll make mistakes like that, and you'll say, this just doesn't make any sense. And you'll go back and you'll say, this is the mistake that I made. So let me show you what I did. I said SPE. You know, I didn't create a teachable moment, but I think that's a teachable moment. I actually made that mistake in real life. So SPE is standard error over X bar times 100%. That's the percentage sign. So to correct this, my standard error then is now that I know the standard percent error, my standard error is going to be SPE times X bar divided by 100. And so that is 56 times 16 divided by 100. And I get 9. So my standard error is 9. That means that the area of this square, given my uncertainties, is equal to 16 plus or minus 9, whatever, square meters or whatever it is. So you need to know how to calculate the standard percent error and then propagate it into some other value like area or volume. You're actually going to be doing volume. And by the way, when you're doing volume, this works exactly the same, except instead of area here, you'll have that as volume, and instead of having 2 terms, you're going to have 3 terms: SPE length, width, and height. And that's all squared. Okay, I'm going to stop here, and then I'll come back and address some other issues.